This is the first lesson from Unit 5 in Advanced Functions, where we make the shift away from polynomials and rationals and towards trigonometric functions and exponential functions. This unit, as you can see here, is got 8 sections to it, plus there's a review, plus I think there will be a quiz as well. Just quickly on that topic about the quiz, today the main goal is to basically look at the very first topic here about what is a radian measure. So what is a radian? And basically, if you think about where we're headed with this, it's sort of like these quiz areas here. So what's the difference between a radian and a degree? How do you convert between radians and degrees? And then, of course, why do we use radians? And I'm going to try to put some emphasis today on this third question about what are the advantages, what's wrong with degrees, and the way that you've learned angles in the past. Why do we use radians now instead? So this is more of a bigger picture. What are the advantages of using this new type of way of measuring an angle? Okay. So the first thing we're going to do here is we're going to look at the radian measure itself. What does this mean? What are we talking when we talk about a radian? So a radian is a different way of thinking about the angles in a circle. So a circle has 360 degrees in it, as you know, which is a complete rotation all the way around the circle. But if I asked you, what is a degree, or where do degrees come from, or why are there 360 of them, I don't think you'd be able to answer. I think you would just say, well, that's the way it is. That's how we count them. That's the number of degrees that are in a circle in a complete length. The reason that 360 is the number that was chosen to represent a full rotation all the way around the circle is because 360 is a number that ancient people really liked. Ancient people liked the number 60 because of how divisible it was. You can divide 60 by 1, 2, 3, 4, 5, and 6. You can divide 360 by all of those numbers plus and more. And because you can divide it so evenly into so many different parts, it was chosen for the same reason that 60 minutes were chosen in an hour. We see the number 60 show up in certain conventions. But of course, there is no reason why we should say, from here over to here is a 90-degree angle, right? Like we could call that whatever we wanted. It doesn't have to be 90 degrees. We could define this as being, a different amount, and then you can set up the circle however you like. Now, the radian is a different way of thinking about angles. Okay, so let's start with the idea that a radian is a measure of an angle. Okay, and so the first thing to understand is that when we talk about radians, we are talking about an angle. Whereas in the past we would say there are such and such degrees in this angle. Right now we'll say there are such and such radians. For example, if let's just use a simple example here, right? So we're going to make a point A, and then I'm going to rotate the point A alpha degrees. Okay, it's going to say, what do you mean by alpha? I'm going to create this slider, and you can see that it doesn't actually, GeoGebra does not default to degrees, because as I will hopefully convince you over the course of the next couple of weeks, radians are actually a superior way of measuring angles. There's all kinds of advantages to them that we'll discover as we use them more. But you can see here that so let's measure the angle, right? So we're going to put a new point O. We're going to angle from A to O to A prime. And you can see that the angle is down there, right? It's like, okay, so here's a very small angle, 0.209 rad. And then we go up here, and there's 1.57 rad, and we keep going, and we get to 3.14 rad. We keep going, we get to 4.7 something, 71 rad, and then we can complete a cycle in 6.28 rad. And of course, the first instinct when you look at this is like, okay, but what possible advantage could this have? I mean, we have very simple numbers to represent these angles, normally speaking. Now you want me to think about a 270-degree angle like this one, and you want me to think of it as 4.7143 rad? Like, that's a very long number with a lot of decimals, and furthermore, it has more decimals if we want to check them, right? I mean, there's no limit to the number of decimals that rads actually have, right? They're irrational numbers. So the bar is pretty high here in terms of, like, you want me to switch from a degree-based mode that I understand to a rad-based mode where the radians are representing like a long irrational number. Let's look at maybe why that would be helpful. So first of all, the rad, I said I would talk about some advantages that rads have, and the first advantage is that a degree has nothing particular to do with a circle. Like 360 degrees is a completely arbitrary number. It doesn't have a special meaning, whereas a rad actually does have a special meaning. And a rad is defined as whatever this angle is here, theta, so that the length A of the arc that subtends the angle is the radius of the circle. So, in other words, if you were to, have a circle with a radius of r, and you were to walk along the edge of that circle, what we call an arc, right? This region here is an arc. And if you were to walk exactly r around the edge of the circle, you would travel 1 rad in terms of the amount of angle that arc has created. So let me see if I can make this point here, right? So let me go back here, and we'll go back to this. And then what I want to do is we're going to trace, we'll trace A prime here. I'll get rid of all these decimals. This is no longer important. I will keep 4, I guess, is reasonable. Okay, so let's trace this. And what I'm going to do is I'm going to draw an arc. Okay, so I'm going to draw an arc, and let's draw an arc to exactly 1 rad. Okay, and here, give or take, whatever, I'll get it as close as I can. Okay, so there you go. That is an angle that is 1 rad. Okay, I got GeoGebra to measure it. Now, if I draw my circle here, so I'm going to draw a circle centered at point O with radius 4. And then I'm going to measure the arc. Okay, and the arc is between A and A prime. Sorry, I need to tell it the circle first. So the circle is C, and then the arc is from A to A prime. Now, look at the arc that I drew. Okay, let's just change its color, and we'll blow it up a bit. So make it red, and we'll just thicken it up. Okay, so this is the arc that joins, excuse me, A to A prime. And you can see that the arc is basically exactly 4 units long, because the radius of this circle is 4. So if you walk 1 radius going around the outside, 1 length of radius is equal to 1 radian, and hence the name, right? Now if I actually specify that beta is 1 rad, alpha, is 1 rad, right? I don't know what I just did. Let me just undo that for a sec. Sorry. Alpha is. Okay, so if I make it exactly 1 rad, look at the value of my arc. My arc has taken on a value of exactly 4. Okay, and this is the important idea with a radian. Now, if we make alpha 2 rads, okay, so let's make alpha 2 rads this time. Notice that the arc now has grown to a size of 8. Because basically I've gone 1 radius, like I've walked 1 radius here, and then I walked another radius to get to there. Okay, and that would be what 2 rads looks like. 3 rads would get you almost all the way around the circle, because of course if you walk 1, 2, 3 radii, you're not actually going to go halfway around the circle. You won't make it, right? Because we know that the circumference of a circle is 2 times pi times radius, which means, 2 pi is like 6.28, right? So we would need 2 pi radius to go all the way around. So it makes sense that at 3 rad, I haven't quite made it. Now, by the way, at pi pi rad at exactly pi, okay, if I go angle alpha is pi rad, notice that pi rad is a perfect match for 180 degrees. And this is the first thing, the first really big important idea to understand, okay, is that 180 degrees is equal to pi rad. And this is connected with the idea that 360 degrees would be equal to 2 pi rad. And of course 2 pi comes from the formula of 2 pi r to get all the way around the circle, right, with the circumference. So this is a hugely important idea. What you think of as 180 degrees, I want you to start trying to think of as pi radians, because they're the same thing. 360 degrees is 2 pi radians. Let's just finish the demonstration, okay? So if I make alpha 4 rad, you notice I go 1, 2, 3, 4. Then if I make alpha 5 rad, I get, I keep moving around the circle, and I've now traveled a distance of 20 around the circle, right? So 4 plus 4 plus 4 plus 4 plus 4. If I make alpha 6 rad, right, it's almost all the way around. And if I make alpha 2 pi, then I do go exactly all the way around. Now you can see it measures the distance as 0 because it's like it's gone all the way around the circle and is now on top of itself. So let's make alpha 2 pi minus 0.001, right? We'll just make it really close to 2 pi. And you can see that now it's a complete revolution of the circle. So what you used to think about as 360 degrees, which is the way that you could go all the way around the circle, we can now think of that as 2 pi radians. What is a radian? A radian is an arc, okay? An arc, which is a section of the circle's perimeter that has a measurement of exactly 1 radius. And of course, how many radiuses or radii do you need to go around a circle? You need 1, 2, 3, 4, 5, 6 and a bit. And that bit right there is represented by basically 2 pi, right? The difference between 6 and 2 pi. If I write down 2 pi, right, it's 6.2832. If we make our angle 6.2832, we will go all the way around the circle, right? It'll be a complete revolution. So this is the idea behind a radian. Instead of thinking about angles as 360 degrees, we are now going to think of them as just 2 pi radians. And we're going to split up the idea of 2 pi the same way that we would have split up 360 in the past. Let's go through and read a couple other things here, and then we'll come back and make some more points about the why behind this. So the arc length and the radius are measured in a unit of length, okay, right, like centimeters. So again, 1 radius right here and 1 radius sorry, going along the circumference are both measured in the same unit, right? So they're both meters or they're both centimeters, whatever it is. 1 radian is the measure of the angle subtended at the center of the circle by an arc equal in length to the radius of the circle. So once again, here's 1 rad, here's 2 rads, here's 3 rads. And you can see that the 3 rads is almost like 180 degrees, but not quite, right? Because of course we know that to get all the way across the circle in a direct way, you would need pi, not 3. Now rad is the unit of measurement for this, but often it's not actually written down. So for example, if you say theta equals 1 or theta equals 2 or theta equals 3, it's understood that you mean rad. So if you want to say degrees, if you want to say 60 degrees, you need the degree sign. If you want to say theta equals 3 or theta equals 3.6154, I will understand that rad is your implied unit. Okay, so basically from now on, if you don't write anything, you're answering in rad. And all of your answers are in rad, by the way. I'm not asking any questions about degrees whatsoever. So I'm going to assume they're in rad. If you need to write something in degrees, like in your communication or something like that, you just make sure you indicate that you're talking about degrees. Now, of course, in order to get all the way around the circle, it takes us 2 pi r. in terms of the circumference of the circle, right, equals 2 pi r. So of course you would need 1, 2, 3, 4, 5, 6, 6.28 rads to go all the way around the circle. Hence, theta is equal to 2 pi is a complete revolution. Okay, so going around the circle completely is 2 pi. Okay, so one complete revolution is 2 pi radians. 2 pi radians is equal to 360, and basically pi is 180 degrees. Pi, what we now think of as 180 degrees, we can just think of as pi. If we're in radians, of course, it's 3.14 radians, because that's what it is. Now, for now, okay, and I really think that this is something that you want to work on, but for the time being, one of the most important things to know, right, we'll just get my little, one of the most important things to know, sorry, my light bulb drawing skills have deprecated since I did all this more in COVID. To convert radians to degrees, so if I give you a measurement in radians, you are going to multiply by 180 degrees, and then you're going to divide by pi. Okay, and that's going to be a simple way of doing this. So for example, if we go back here, and let's say I've got this angle here, 2.09 rad, right? I don't really know where 2.09 rad is yet because I'm very new to this, right? If I want to convert that into degrees, I could go so the angle. So obviously I'm on GeoGebra, right? So one thing I could easily do is I could just change the settings. I just go from angle unit over to degree, and you can see that the degree is 120, right? So 2.0944 rad, I switch it to degrees, 120. How do we do that if we're just, calculating ourselves? Take 2.0944, multiply it by 180, okay, you get 377.82, divide that number by pi, you get 120, okay? And that is how you can convert from radians to degrees. Now, because you're new at this is something you're probably going to do a lot. You're probably going to convert back and forth between degrees and radians a lot because you're very good with degrees. You're not, you're just learning radians. So this is useful. I would encourage you, though, as time goes on, to try to get past this idea that you're just converting all the time, because what you ultimately want to do is actually understand radians. You don't want to constantly be converting it back to degrees so that you can do your calculation. In any case, it's a very useful ability, and for the first little bit, you probably will find yourself doing a lot of converting. So let's just review how to do it. If you have degrees and you want to go to radians, you simply multiply by pi and divide by 180. So for example, if we wanted to say, let's just do the exercise in reverse here, so we'll just switch it to degrees. We'll say we'll measure, 152 degrees. What would that be in radians? So I take 152 degrees, I multiply it by pi, and then I divide it by 180. Okay, and when I do that, I get 2.6529 rad. If we go back to rad, 2.6529 rad, right? So it's easy enough to convert them back and forth, and I do think for the first little while that is the way you're going to approach this. Okay, you can use this to convert to make it more familiar to yourself as you're getting the hang of this. It's just one of those things that, again, if you're shooting for the level 4s, the level 4 pluses, and so on, you are going to want to move past simply converting it all the time and actually try to do your thinking in radians. There are reasons to do that. You just have to give me some time to make the case to you. Now, for here, right, so again, really simply, if you're radians to degrees, multiply by 180 over pi. If you're degrees to radians, you multiply by pi over 180. So here, right, for example, it's asking us to convert the following things from one to the other. So in the left here, we have a bunch of different angles in radians. On the right, we have a bunch of different angles in degrees. Now, it seems as though you're going to need a calculator for this because, we need to multiply by pi, divide by 180, whatever. But none of these questions should require a calculator. The reason being, typically when you give an answer in rad, you leave pi in the answer. Okay? So not always, okay, not always, but often, oh, sorry, what happened? here? Sorry, it's like it doesn't know what I'm drawing. Sorry. Okay, yeah, there we go. Okay, so often answers in RAD often contain pi. Okay, and so like what you see here, for example, in the left column, notice that pi is in all of these angles. So really, when you think about it, if pi represents 180 degrees, right, and we know that pi does that because we just went through how, 2 pi is a whole circle, pi is half a circle, and so on, then pi over 2, I mean, just think about it. If a half a circle is pi, right, then pi over 2 would be the quarter of a circle, and that would represent 90 degrees, right? So pi over 2 is the same thing as 90 degrees. It's a right angle, pi over 2. Let's go back and just show on my drawing for a second. So convert it back to radians. Now I'm going to type in alpha equals pi over 2. And what does it draw? I mean, it draws a perfect right angle, right, which you can see with the square there, because pi is the complete thing from top to bottom. So pi over 2 would be just to get you up to the top here, right? You'd make a 90-degree angle, and that's pi over 2. Over here, pi over 4. Okay, well, what happens if I split 90 degrees in half? I get 45 degrees, right? I mean, that's straightforward. What about pi over 3? Okay, so once again, pi represents the whole semicircle. Pi over 3 represents splitting it into 1, 2, 3 boxes. Well, if pi represents 180, then pi over 3 is 180 divided by 3. It represents 60 degrees. Pi over 6, for the same logic, would represent 30 degrees. Okay, and hopefully this makes sense to you. If it doesn't, then go over to pi over 6, for example, and use your converter. Multiply it. Sorry. I'm just getting used to this tablet again. Pi over 6 times, 180 over pi. What happens? Pi and pi cancel. You get 180 over 6, which we know is 30 degrees. Sorry, 30 degrees. Okay, and that's going to be how I'm doing this. Basically, I'm substituting 180 in my mind for pi. So just one more time, let me write that out properly. So the strategy here is, right, pi over 6, I'm supposed to multiply by 180 over pi, and when I do that, pi cancels, and I get 180 over 6, which is 30 degrees. Oh man, I'm sorry, this thing will not let me move further than here, so maybe I can just move it over a bit, sorry. Okay. Now, going the other way, okay, so it says change the following to radians, 270. Let's start with a little bit of an easier one first. So let's look at, for example, 240. Oh, well, I guess it doesn't matter. 270 is fine. Okay, so 270, okay, according to our strategy, we're supposed to multiply it by pi and divide by 180. What am I actually doing here? I'm taking 270 over 180. I'm finding out what that is as a fraction, and then I'm just leaving pi attached to it. Now, if you divide 270 and 180, if you divide them both by 90, you will get 3 divided by 2. And so, what is this first angle? It is 3 pi over 2. Okay, and that would represent a 270 degree angle. Let's confirm that by typing in alpha equals 3 pi over 2. And you'll see that the angle is a perfect 90 plus 90 plus 90, which is a 270 degree angle. Right? We switch it back to degrees and see that that's the same. So a 270 degree angle is 3 pi over 2's. A pi over 2 is a 90. So 3 of them makes 270. How about 240? Right? 240 is the same thing. So we got 270. Let's just write it over here. Okay, so we're going to do 240 times pi over 180. Well, 240 and 180 are both divisible by 60. So we'll divide both of them by 60. We get 4 over 3 pi. And that's going to be our answer here. So you can say 4 pi over 3, or you can say 4/3 pi, whichever. They're both the same thing. Okay, so that's what you're doing there. For the next one, right, we'll write 150 over 180 times pi, and then all we got to do is reduce it. How do you reduce 150 over 180? You divide them both by 30. The top one becomes 5, the bottom one becomes 6, and pi simply stays there, right? So 5 over 6 pi. Next one, 120 over 180 pi. Okay, we are going to divide them both by 60. 2/3 pi. Okay, so all you're doing here is just, putting in the conversion formula and then reducing the fraction. Okay, that's the strategy. So put in the conversion, reduce it. What's 225 over 180 times pi? Now, 225 and 180 are both numbers that are divisible by 45. There are 4 45s in 180. There are 5 45s in 225. So our answer is 5 pi over 4. We'll just confirm that last one. If we change alpha to 5 pi over 4, we get this 3.927 rad. But if you change that to degrees, 225, right? So 5 pi, 5 times pi over 4 is equal to 3.927. Now you can write 3.927, but you can also write 5 over 4 pi. And I would suggest it's easier to write 5 over 4 pi than to write 3.927, right? It's easier to understand this. This is actually easier to understand versus 3.927 rad, right? Which is also right, like they're the same thing, but this is like a smarter way of doing it, right? Where you're writing it as a fraction of pi. Okay, example 2. Convert the following to radian measure, simplify with pi. Alright, so again, same thing. We're going to do 100 times pi over 180, and we get 100 over 180 times pi. We're going to reduce that. I can divide them both by 20. I get 5 over 9 pi. And that's my answer, right? That's as far as I can go. 210 over 180 times pi. I can divide both of them by 30. 7 over 6 pi. And that's how you would represent either of those things as representations of in radians. Okay, so you can take degrees and convert them into radians by multiplying by pi, dividing by 180. Practically, you're going to leave pi in as almost like a variable. Right now, pi is a number, but rather than write out the long decimal, we just write a fraction of pi instead. Okay, how do you convert to degree? So again, you take your 4.81, you multiply it by 180, and then you divide it by pi. Now these ones are not going to, we're not going to leave pi into the answer here. We're going to actually calculate it. So, this one, for example, it just says 4.81 rad. We're going to multiply it by 180. We're going to divide it by, divide it by pi. So times 180 divided by pi, and we get it's a 275.6 degree angle. So just to test that, make alpha 4.81. We'll convert to degree, right? 275.5927, which is exactly what we got, calculating it the other way. So 275.6, round to one decimal place, right? So 275.6 degrees, okay? 3.2 rad, I mean, if you just think about where 3.2 rad is, so remember, right here would be 3.14 rad. So 3.2 rad is going to be slightly bigger than 180. Slightly bigger, right? Because 3.14 we know is 180. So 3.2, we'll just test it. So, again, to convert it, we're going to take 3.2, we're going to multiply by 180, we're going to divide by pi, and we'll get the answer. Okay, so 3.2 3.2 divide by pi. And I get a number that's very close to 180. It's slightly bigger than 180. 183.3 degrees. Okay. I've lost my 183.3 degrees. Okay, and that would be converting that radian to degree. Now again, to convert to degree, I mean, all of these ones, this is you know, it becomes kind of just the same thing over and over again, right? I got 5 pi over 3. I'm supposed to multiply by 180, and I'm supposed to divide by pi. So what's going to happen here? Of course, the 2 pi are going to cancel, right? And I'm going to be left with 5 times 180 divided by 3. Now, I'm going to do that as 5 times 180 over 3. Remember, order of operations says you have to do multiplication and division at the same time. So whichever way you want to do this, you can divide 5 by 3, or you could divide 180 by 3, or you could multiply 5 times 180 and then divide the answer by 3. But in my opinion, why don't we divide 180 by 3 first, which is something we can probably do mentally, right? We get 180 divided by 3 is 60. 5 times 60 is 300 degrees, right? And then I don't really need a calculator to do something like that. 5 pi over 3 is 300 degrees. Let's test. Put alpha equals 300 degrees, and then we're going to convert it back to radians, and we get 5.236. Now what the heck is 5.236? I don't recognize that. So remember, you have to actually check, what is 5 pi over 3? Ah, I see. 5 pi over 3 is 5.236. So, you know, when they say 5 pi over 3, another way of thinking about this is 5.236 rad, right? Those two things are equal to each other. It's just that when you write it with pi, you're being exact because you're keeping every decimal. When you write it as 5.236, you're rounding it a little bit, right? It's not a perfect match there. Okay, we'll convert the other ones quickly. So 7 pi over 4 times 180 over pi. Once again, I'm going to do it in the same way. 7 times 180 over 4. Well, 180 divided by 4 is 45. And 7 sets of 45 is, what is that, 315. Right? 7 sets of 45 would be 315. Just check my work here. 7 pi over 4 times 180 divided by pi, I get 315. Okay, which is just simplifying the expression. Okay, 5 pi over 12. 5 pi over 12 multiplied by 180 over pi. Once again, I'll think about it as 5 times 180 over 12. I know that in 180 there are 15 sets of 12, right? Because the 10 12s make 120, and 5 more make 60, so 120 plus 60 gives me the 180, and 5 times 15 is 75. Okay, so 5 pi over 12 is equivalent to 75 degrees. Last one here is 11 pi over 6. I'm going to move the screen because this is going to give me a problem here in a second. I'm too close to the edge. Sorry, I'm really... Oh, right, sorry, I can't do that. Okay. Gradually getting the hang of this thing. Okay, so here... sorry, not multiply. Multiply. Okay, 180 over pi. Similar sort of thing. 11 times 180 over 6. 180 over 6 is 30. 11 30s is 330 degrees. Okay, so this first page is, I think it's a really important page to get comfortable with. As I say, in the long run, I want you to look at 7 pi over 4 and know what it means without having to convert it. But of course, I recognize that on day one, you know, you're not necessarily going to be there. But you know, as you use it more and as you understand it more, hopefully this 7 pi over 4 starts to make sense to you by itself, right, without having to compare it to degrees or something else you already know. In the meantime, I think this page is super important for getting familiar with how to move back and forth between this new radian thing and the more comfortable degrees. Okay, and of course it's fine to convert as you need to. It's just like I say, people who get 80s, 90s and up are people who ultimately transcend the need to convert all the time. They get it because they understand what the 7 pi over 4 or the 5 pi over 12 or whatever actually means. So that's what you should set as your target. Now, the last page of this here talks about finding some missing qualities and then like finding some, solving some problems. And I said I would discuss with you the advantages of radians, and so we've already covered one. The first advantage of radians was up here, which is that it actually has a definition that is connected to the circle, right? And essentially the idea was, remember, if I go with an arc length of exactly 1 rad, right? So if I go back here to make 1 radian, or at least as close to 1 radian as I can, alpha equals 1. 1 rad means my arc is 1 radius, okay? And that's, remember, the definition of a radian. It's a rad, and it's it's exactly 1 radius. Now you might be thinking, like, is that just a coincidence or something like that? What if I made the point 5 units away? Let's make the point 5 units away, and then we'll make the circle with a radius of 5 instead. Now notice that if I make the circle bigger, the arc is bigger, it's a 5 now, but the rad is still the same. It's still 1 rad, right? In a circle of size 4, 1 radian would be 1 arc of length 4. In a circle of size 5, 1 radian would be an arc of size 5. If I shrink this down or raise it up or whatever, the radian and the radius are always going to be connected. So here, right, it's a radius of 2, the arc is 2, the rad is 1. It's a radius of 3, the arc is 3, the radian is 1. 4, 4, 1, 5, 5, 1, 6, 6, 1, and so on, right? So like, it doesn't matter how big the circle is. 1 rad is always how far you would get if you walked 1 radius along the circumference, okay? And that's the first reason that radians are a better unit than degrees, because their definition actually means something. 360 degrees doesn't mean anything. It's simply a convenient number to think about splitting the circle up into. But if you really push on it, why do we measure a circle out of 360? I doubt you can answer it. It's just the way it's done, right? It doesn't actually connect to anything about a circle. A radian does connect to something about a circle. It connects to arcs. For that reason, radians are actually very good at answering questions that have to do with arcs. Right? So like these 2 questions, for example, are ones that we could see that it's useful for. The other really big advantage of radians comes in the rate of change, and I will do a demonstration for that at the end, just to give you a brief idea. In the meantime, let's take a look at how radians really shine in terms of connecting an arc, which is a length around the circle, to an angle. So remember, the only formula you need is theta equals arc over radius, and that's the definition of the angle. It's actually quite clever when you get a chance to think about this. If I asked you this question at the beginning of class today in a group, let's say we did it in a group, a board thing, and I told you that this angle was such and such degrees, and I ask you, what's the length of this arc? You would be able to do it, but probably not right away. You probably have to go through a series of steps to figure out what's the whole circumference, what's the angle, what's the ratio of the angle to 360, and that ratio would be the same as the arc to the circumference. But here, right, with radians, this becomes very, very simple. Theta is here, the arc is around the outside, and the radius is right there. So theta equals arc over radius is simply, let's just fill in what we know for this first question, right? 2 equals arc divided by 6. So arc is 12, right? It's literally a 1-second question to answer what is the length of that arc when you're working in radians. Again, let me just demonstrate this one quickly by going back to here. Let's make our circle radius 6 like they did. Let's make our alpha 2 rad, and what is the length of the arc? It's 12. It has to be 12 because remember, every rad is exactly 1 radius of movement along the outside. So like 1 rad, sorry, this is tricky. 1 rad is here, would be 6, right? This is 1 rad. And then the other rad is over here, and this would be another 6. 6 and 6 make 12, right? So it's radians are very, very good at answering these kinds of questions where we're looking at the arc or the angle. Let's try another one. Here it says we'd use the same formula. Theta equals arc over radius. Okay, this time we don't know theta, but we do know that the arc is 45 and we know that the radius is 10. Thus, the angle is 4.5 rad. Now you don't have to write rad, but I'm going to write it just for our notes, right? Theta is 4.5 rad. Let's demonstrate this one the same way, okay? So I'm going to make the circle size 10. I'm going to make the arc 45, so you can see the arc here is 43. We'll just get it to be a bit bigger, 44, 40, yeah, okay, so 44.9946, right? And there it is at 45. And you can see that the arc, the angle here is 4.5 rad, right? 10, 10, 10, 10, and then a half. And that gets you all the way to where we are, right? So you can get the angle based on the arc really, really quickly. Last one, suppose we don't know the radius of the circle. We know theta equals arc over radius. And theta is equal to 3.2. And the arc is equal to 28, but the radius is unknown. So we go 3.2r equals 28. R equals 28 over 3.2. So let me just calculate that quickly. So 28 divided by 3.2, I get 8.75. So I'll just write it up here, 8.75. And to confirm that, right, let's draw the situation one last time. So point A, we'll put it at 8.75, 0, okay? And then we're going to, it needs an angle of 3.2. Whoops. Okay, so if alpha is equal to 3.2. And you can see that if it's 3.2 rad, it has an arc of 28, and the radius is 8.75, right? We're exactly 8.75 away from the middle. So this is another area where radians simply excel, right? I mean, the equivalent questions in degrees are, no, they're not necessarily hard, but they're slower for sure, right? Radians is a very convenient unit whenever you're talking about arcs, which is the second big advantage that they have. So advantage number 1, they have a definition that is connected to the circle itself. Advantage number 2, they are very good at solving any question involving arcs. Let me show this one last time. It says the end of a 100 centimeter long pendulum swings through an arc length of 5 centimeters. All right, so we have a point of rotation. We have a pendulum, right? And it swings back and forth this way and this way. And the entire arc length down here is 5 centimeters, right? So it basically ticks back and forth, right? So it swings this way and then that way, and its arc length is 5 centimeters. Its radius is 100 centimeters. Find the radian measure of the angle through which the pendulum swings. Express the radian measure in exact form and an approximate form to the nearest hundredth. Okay, so let's review how to do that. So the formula is always the same. Theta equals arc over radius. In this case, theta is an arc of 5 divided by a radius of 100, and therefore theta is equal to 0.05 rad. Okay, what is it saying with exact form and approximate form? I don't know. This is both exact and approximate, right? I mean, we didn't have to do anything. We didn't round anything. We didn't need pi or anything like that, right? So the end of a 100 centimeter long pendulum swings through an arc length of 5. The arc is 5. The radius is 100. We simply do the arc divided by the radius, and that gives you the angle. Okay, so again, very straightforward. There's not much to these questions, right? I mean, it's pretty much a simple formula that you're just going to use to answer them. Now, this last one is a bit of a different animal, okay? And these revolutions per minute, you can see in the, just going to go back to this for a second. For the quiz, I have a note here about arcs. Well, those are pretty easy, right? This is theta equals arc over radius. That's not much to that, as you just saw in the questions we just did. But this one with the angular velocity is a bit more challenging. And let's just go over angular velocity for a sec. Angular velocity is the concept of how quickly something spins. Okay, so the way you represent it is with this lowercase omega, which looks like that. It's kind of like a W with its sides jutting out. I'll just put in brackets. This is omega, and it represents angular velocity. Now, what is angular velocity? Is simply the speed of rotation. So how quickly does something spin? Now, you may have seen in your car, depending on what kind of instruments your car has, right? It might have a certain RPM, right? And RPM is revolutions per minute, is how many cycles the engine can do in 1 minute, right? And that's what this represents. It's a speed of how quickly a periodic thing, an engine or a rotating object, goes through its cycle. So how quickly something rotates around. Okay, now so angular velocity, the challenge here is that angular velocity can be understood in two different ways. So it can be angular velocity, let's just write it this way. Angular velocity, we can write it two different ways. RPM, which is one way of expressing it. How many times does the object complete a revolution every minute? So how many times does it spin in 1 minute? So you can see this, this furnace, whatever, spins at 1,700 times every minute, right? So like 30 times every second. The other way you can talk about it is in rad per second. Okay, so this is what. So angular velocity, you can discuss it in revolutions per minute, or you can discuss it in radians per second. They are the same unit. It's kind of like saying I was driving down the highway at 100 kilometers an hour versus I was driving down the highway at 33 meters per second. They're both describing the same speed. They're just like a different way of saying it, right? Like when we're in a car, we're used to talking about kilometers per hour, but if we're used to a sprinter or our own, like sprinting speed, we're probably talking about meters per second, not kilometers per hour, right? I mean, it depends. So when you talk about angular velocity, how do you convert from RPM to rad per second, basically, is a question like this. So let's do it like this way. 1725 rev per min. Okay? What I'm going to do is I'm going to use the idea that 1 rev equals 2 pi rad. Now, what's the idea there? A revolution is a complete go around of a circle, and we know that when you're talking about radians, every revolution, that 1 revolution is a complete go around the circle is 2 pi rad. So we're going to take revolutions per minute and we're going to multiply it by 2 pi. So let's multiply by 2 pi. So we're going to get 3450 pi rad per minute. Okay, and basically what I did there is simply took 1750, multiplied it by 2, and really multiplied it by 2 pi. Now I'm not going to multiply it by 2 pi with all the decimals. I'm just going to leave pi in my answer, right? I mean, there's no reason to be putting pi in and computing its decimals, right? You just leave it as a symbol in your answer. Now, look at what they asked for. They wanted radians per second. I gave radians per minute. So I know there are 60 seconds in 1 minute, right? So if there are, so basically to finish the question, I've got to, instead of talking about it per minute, I've got to divide it by 60 in order to get seconds. So 3450 pi divided by 60, right, is going to be giving me rad per second. Okay, and just to simplify that, I mean, we can actually at least simplify the equation part. So 1725 to multiply it by 2, and we're going to divide it by 60. And we get 115 over 2. So we could just leave it like that, I think. 115 pi over 2 rad per second. Now, I think it asks you to give the approximate answer. So this would be the exact answer, right? Because it contains pi, because pi's still in it. Now, if we want to give the approximate answer, we would do the same thing, but we would put in 3.14159, etc., etc. Best to use the pi button if you have it, but 3.14159 will do it otherwise. Okay, so 115 over 2, so p times pi, 180.64. What is it? Said nearest hundredth, right? So that's 2 decimals. So 180.64. Sorry, too close to the bottom of the screen again. 180.64 rad per second. So let's just summarize this with the following. If we want to go from RPM to rad per second, we are going to multiply by 2 pi and divide by 60, right? That's going to take whatever you're doing in revolutions per minute and change it into rad per second. So for example, 1725 revolutions per minute, we're going to multiply it by 2 pi over 60, and we get 180.6416 rad per second. Suppose we had rad per second, and we wanted to convert it to RPM, we would just do the opposite. Multiply by 60 and divide by 2 pi. Now realistically, we could simplify this, right? Pi over 30 and 30 over pi. Like, you don't have to do the 2 and the 60. You could make it simpler, right? I mean, but it might be easier to remember it as 60 and 2 pi because of the fact that there's 60 seconds in a minute and 2 pi rads in a rev. In any case, we could take our 180.64 at the end here. 0.64, we could multiply it by 30 over pi, and it comes back as the 1725 RPM that the question had. Okay, so if you need to convert from RPM to rad per second, this is how it's done, right? It's a fairly simple conversion. It's worth trying to think through why it works this way, so that you can like repeat the formula without having to just memorize something you don't understand. I'm going to end here with a very short demo of why radians are, one last argument about why radians are a superior unit and why you didn't really see them until now. If they're such a superior unit, why did you learn degrees first, right? So here's a graph of sine x if we write it in degrees. And you can see that sine x, when we write it in degrees, it sort of waves up and down, and it comes back to where it started by 360. Now, like we did at the beginning of the year, we can make a tangent to the graph, and that tangent has a slope, right? And if I were to check the rate of change, right? So right now you can see the rate of change of this graph at this moment is 0.01618. Now, suppose I made a second point that had the same x value as a, but as a y value, instead it tracked the rate of change. Okay, and I'm going to trace this thing. Now watch the rate of change, okay? It's positive, positive, positive. It goes to 0. It becomes negative, 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 negative. It goes to 0. And then finally, sorry, just get rid of those. And then it goes positive, positive, positive again and stops. So what's the issue here? If you look at B, right, look closely at B, you know, for all I can tell, nothing's happening with B, right? It's like it's just looks like a flat line, because these slopes, when you're talking about degrees, these slopes are so small that you can't appreciate the two graphs at the same time. Let's zoom in a lot, like so much so that the original graph now looks like ridiculously large. It just looks like a bunch of vertical lines now, right? And let's try the exercise again. So watch the graph that gets created now when I check the rate of change of the original at all these different values. So the rate of change is 0, and then it goes negative, and then it goes back to 0, and then it's positive, and then it caps out again. Now, you may recognize this wave that I've just created as cosine, right? Sine starts at 0 and heads up towards 1, whereas cosine starts at 1 and heads back towards 0. And so what you can see here is that sine and cosine are related in terms of their rate of change. Cosine describes the rate of change of sine. Now, unfortunately, if you're working in degrees, this relationship is kind of messed up, because as you can see, there is a nice cosine graph here, which our second graph created, but we can't actually appreciate the two graphs on the same scale at the same time. If we can see the sine, we can barely see the cosine at all. And if we can see the cosine, the sine, just looks like a bunch of vertical lines. It's basically so big, right, that trying to do that this way really doesn't work very well. Now let's do an alternative. Let's type sine x instead of sine x degrees. And you'll notice that GeoGebra by default draws sine as not going all the way to 360, but rather just going to 6, a little bit past 6. Now, can you guess what number past 6 it's going to go? Right? It's going to go to 6.28, or more realistically, 2 pi, right? Because it takes 2 pi, we understand, to complete one cycle. Okay? 2 pi is one full revolution. Now watch the same thing I did before, where I track the rate of change, okay? Except this time, my unit is radians. And instead of taking 360 degrees to complete a revolution, I only take 6.28 radians. Okay, what's the difference? Now this time, right, if you look at that graph, the graph of the rates of change, it's a perfect match for cosine on the same scale that it is for sine. So if I draw cos x next, right? So cos x looks like that, and you see that if I choose radians as my unit, then cosine is a perfect representation of the rate of change of sine. And that is a deeper reason, a more important reason, why radians are the superior unit. Because when you are talking about rates of change, degrees are so big that the rate of change is ridiculously small. The rate of change is always like 0.01 at best, right? It's a very small number. Whereas when you're dealing in radians, the rate of change oscillates between -1 and +1 the same way the parent function does. So it's a perfect unit to measure the rate of change of a trigonometric function. And since in advanced functions we are talking about rate of change, there is a good reason why radians are the superior unit once again. Calculating rate of change with radians is much better, and just the numbers are more in the same ballpark, so to speak, than when you're working with degrees. Rate of change and degrees really do not work well together. Okay, whereas radians, they do. So to summarize for today, I said there would be, so I showed you what a radian is. We talked about how do you convert versus radians and degrees, right? The two ways to convert it. And I shared with you 3 advantages of radians. To recap them quickly, number 1, its definition is connected to the circle. 1 rad is equal to 1 arc of length r. Secondly, radians are very good at any question that actually involves arcs. So if you're looking at a question where an arc is an unknown, or it says, you know, you're walking around a circular track, the track has a radius of 100 meters, you walk 450 meters, what is the angle you walked, right? How much of an angle have you gone through? Not an easy question necessarily with degrees, but a very straightforward question with radians. So radians are a good way of dealing with questions involving arcs. Finally, and most challengingly, but also most importantly, radians are a greatly superior unit for rate of change. If you're studying rate of change with degrees, the numbers are always irritatingly small, right, and difficult to graph at the same time as the original parent. Whereas with you're talking about radians, there's a perfect match between the original function and the rate of change function, where they both have the same amplitude, they both have the same period. It's just that one is sine and one is cos, right? And that is, so really that third reason, the rate of change reason, is the one I want you to focus on here for thinking about, you know, communication later. Okay, so this has been lesson 5.1 on radians. After this one, we will start to work with you know, more typical trigonometric sorts of activities, like drawing the functions, sketching them, doing modeling, how do you solve different angles and whatnot. But of course, this lesson is crucially important to grasp what a radian is and how we can go about using them.